Welcome to the training session, Why GaN for DC to DC Power Conversion. eGaN devices from efficient power conversion offer improved performance over silicon MOSFETs, enabling a new generation of power converters offering higher frequencies, efficiencies, and densities than ever achievable before. The adoption of artificial intelligence, 5G, and big data are leading to more intelligence, but higher current requirements for the XPU, as well as more silicon content. Space on a server board is extremely precious, and servers, especially those designed for performing high-end computational functions such as artificial intelligence, are demanding more power. This poses a challenge to the standard 12-volt input power distribution network infrastructure that struggles to deliver the increasing power and required power density. To solve this challenge, high-power artificial intelligence cards, hyperscale systems, and servers are moving from a 12-volt input to 48 volts. The benefits of a 48-volt power distribution are easier delivery and distribution of higher power, solving the challenges facing the current ecosystems like cabling and connectors, distribution losses, and total cost of ownership. It builds on the industry's proven 54-volt or 48-volt infrastructure. The entire system efficiency is improved due to 1/16 of front-end distribution losses. And you can deliver 4 times the power transmission or 1/4 of the current. This is how the new server architecture will look. In this new topology, the input of the server board is 48 volts. In this block diagram, the intermediate voltage is 12 volts. The most efficient solution to convert from 48 volts to point of load, which is about 1 volt for CPUs, GPUs, or XPUs, is a 2-stage conversion, 48 volts to an intermediate voltage, and the intermediate voltage to the point of load. The intermediate voltage can be 12 volts. That allows to power legacy 12-volt loads, or it can be 5 volts, a voltage that offers a huge efficiency advantage over 12 volts. In this new architecture, a non-isolated, unregulated 48-volt DC to DC converter is mounted on the server board and converts 48 volts to 12 volts, or 5 volts, that is used as the input voltage for the second stage that powers the CPU through digital multiphase controller and power stages. eGaN FETs increase power density and efficiency for the front-end conversion, 48 volt to 12 volt, or 48 volts to 5 volts. Additionally, the AC to DC power supply that remains on the server rack is also converting rapidly to GaN FETs or GaN ICs on both the primary side and the secondary 48-volt side. EPC's 200 volts of transistors is ideally suited for this synchronous rectification application. How do we get from 48 volts to 12 volts? The most common topologies for this conversion are buck converters, resonant LLC, and switch capacitors. We will now analyze the pros and cons of each of these solutions. Buck converters enable a regulated output voltage. This topology is very simple and requires very few components for low total solution cost. Power density is very high and the design is scalable and supports multiple phases for high power. Buck converters enable the smallest size, lowest component count, and the lowest cost. This slide proves it by showing on the left a 300-watt converter in a 1/16 brick size featuring our EPC 2053 eGaN FETs in a 2-phase configuration, and on the right a 180-watt converter in a very small size, 14 millimeters by 9 millimeters, featuring our integrated power stage. Efficiency for both solutions is around 97%. The solution is scalable for higher power, as proven by this 3 kilowatt 4-phase design using EPC 2206 FETs. This is a typical design for a mild hybrid car, and the efficiency is around 96%. 100-volt eGaN FETs and monolithic power stages are the best solutions for buck converters due to the best figure of merit for hard switching applications, their small form factor, and their exceptional thermal conductivity. They enable 33% higher efficiency compared to silicon MOSFETs, while saving about 33% of the space. A switch capacitor solution can also convert from 48 volts to 12 volts. This topology is widely promoted by several suppliers such as STMicro, Infineon, Renesas, ON Semiconductor, Richtech, as well as others. Switch capacitor topology in this example uses 25 volt and 40 volt FETs. This slide shows a 4-to-1 switch cap converter. As you can see, this solution requires several components: 10 switches, a complex and a smart controller, complex drivers like floating or isolated drivers, and a charge pump. This solution is far more complex than the buck or the LLC topologies, and it has lower power densities. It can, however, supply slightly better efficiency, around 98%, for systems less than 600 watts, but it is limited in current and does not support multiple phases. It also cannot, without doubling the number of components, go to voltages lower than 12 volts from a 48 volt input. This is a typical switch cap solution for 500 watts. For 300 watts to 600 watts, switch cap is a good design and the size is okay. But below 300 watts, a buck solution is far smaller and cheaper due to less components, like we saw in the previous slide. Efficiency up to 500 watts is very good, above 98%, and can be further improved with eGaN FETs, as shown in the green and blue waveforms. However, the switch cap solution is limited in power and cannot handle more than 600 watts. The LLC resonant solution is based on a transformer, a full bridge or half bridge rectification on the primary side, and a synchronous rectification on the secondary side. The design is simple and allows for very high power density. The topology supports multiphase for higher current, and with the correct transformer design and the right FETs, efficiency exceeds 98% and remains 98% even at very high power, like 1 kilowatt. Finally, it's easily adaptable for different output voltages by changing the transformer ratio. The LLC is the best solution for over 600 watts and achieves 98% efficiency. Switch capacitors have limitations above 600 watts. Buck converters can deliver a kilowatt or more, but the efficiency is generally lower, around 97%, and there is a big inductor and a big heat sink that are required. Even in this case, eGaN FETs and ICs enable a small and efficient LLC converter due to very small form factor, less losses, and 1 megahertz operation. The low gate capacitance, low output charge, and low on resistance, and exceptional thermal performance of the eGaN FETs are the key to delivering 900 watts and achieves 98% efficiency at a power density exceeding 1,500 watts per cubic inch without a heatsink. To sum it up, switch capacitors are limited to 600 watts, and it's a very good solution between 300 and 600 watts with an efficiency higher than 98%. Buck converters can have a regulated output and are smaller and cheaper below 300 watts. They could do more than 600 watts, but efficiency would be lower than an LLC, and inductor size and thermal management is more challenging. The LLC is the best solution for higher power, that is greater than 600 watts, and offers an efficiency around 98%. Lowering the intermediate bus voltage from 12 volts to 5 volts is a second shift that's rapidly occurring. This is particularly the case for artificial intelligence systems using several GPUs, where voltages can be as low as 0.6 volts and the current can be higher than 1,000 amperes. This shift is driving a change in technology. The point of load converters that used to be 12 volts in to 1 volt out and relied upon trench MOSFETs are now shifting to 5 volt to 0.6 volt point-of-load converters using monolithic BCD-MOS power stages. These BCD-MOS power stages can go to higher frequencies, making the point-of-load smaller and able to be placed much closer to the GPU or CPU, even below the heatsink. 5 volt input and higher switching frequencies above 2 megahertz allows the point of load to be much closer to the GPU or CPU. This reduction in distance can reduce the resistance between the point of load and the CPU or GPU by as much as 350 microohms. At 1000 amperes, that's a 350 watt reduction in losses. How do we do 48 volts to 5 volts? Well, switch caps are too complex for an 8-to-1 reduction. They have double the complexity of a 4-to-1 conversion. Buck converters can do 48 to 5 volts, but the efficiency will be lower than the LLC, and the inductor size and thermal management is more challenging. The LLC is the best solution for 8-to-1 and 10-to-1 reductions and can deliver power over 600 watts with the highest efficiency and the highest power density. This is our 900 watt LLC reference design. The solution can easily be upgraded to higher power. The design uses 4 EPC 2053 GaN FETs for the primary side full bridge rectification and EPC 2023 for the secondary side FETs. Thanks to the high 1 megahertz switching frequency and small FET form factor, the design has a very small size, 51 by 37 millimeters. Thanks to the excellent RDS on and figure merit of the FETs, the design can deliver greater than 98% efficiency. Let's look now at the specific portfolio for 48 volt DC to DC. All the applications we mentioned required a 48 volt input power, and this requires 100 volt devices. This voltage range is the sweet spot for GaN technology. In all topologies with 48 volt input, the highest efficiency comes with using our GaN devices. Here you see a full range of 100 volt FETs from EPC with on resistance ranging from 20 milliohms to 2.5 milliohms. Gate charge is very small, from 1.7 nanocoulombs to 11.8 nanocoulombs. QGD is also very small for very low switching losses, and QRR is 0. The device area is ultra small, from 1 millimeter squared to 7 millimeters squared. The BGA devices, except for the 2051, can nest so that the same layout can accommodate different FETs to allow easy and flexible upgrade for efficiency or load current changes. If we compare the performance of GaN FETs versus the benchmark silicon MOSFET, the RDS on of the device in this example is 22% smaller despite the higher voltage rating of the GaN device. QGD is 84% smaller, QG 60% smaller, and QRR is 0. Additionally, the GaN FETs are 1/3 of the size. Overall, GaN devices deliver 5 times the power density. Since GaN is a lateral device, it's very easy to integrate solutions beyond discrete devices. Here's a new addition to our family, a fully integrated power stage in a super small size. The E-Power Stage, digital in and power out family, simplifies design and further reduces size. The device is very small, only 10 square millimeters, and integrates drivers, level shifter, half bridge FETs, and bootstrap. The maximum input voltage is 80 volts, and the maximum current at 1 megahertz is 12.5 amperes. This level of integration improves efficiency. Here you can see the efficiency improvement between integrated eGaN power stages and a discrete solution with one driver and two eGaN FETs at 1 megahertz and 2.5 megahertz. The green curve is the integrated solution, and the blue is the discrete solution. For 48 volts to 12 volts at 1 megahertz, the integrated solution delivers greater than 96% peak efficiency and up to 2% efficiency improvement at 12.5 amperes. The improvement can be explained by three factors: the matching of the gate drivers with the power FETs, no parasitics like ground loop, common source, and gate drive inductances, and thermal balancing of the two output FETs. The improvement is even bigger at 2.5 megahertz, where an integrated solution can deliver at least 3 extra amperes versus the discrete solution. At higher switching frequencies, GaN technology with ultra-low switching losses widely outperforms silicon MOSFETs, generally limited to 91% efficiency at best at 1 megahertz for 48 volt to 12 volt conversion. Now let's look at some success stories. As we discussed, the LLC is the best solution for 8 to 1 or 10 to 1 conversion ratios. Here are 3 solutions, 2 already shipping in volume, all using 100 volt eGaN FETs. The 2 modules on the left from different vendors convert from 48 volts to 5 volts and deliver 300 watts in a super small 27 by 18 millimeter size. The module on the right is 600 watts, and the size is double the size of the other 2. All 3 modules reach a very high power density of 1,700 watts per cubic inch thanks to eGaN FETs enabling 1 megahertz operation. This is a TI reference design that delivers 600 watts from an input voltage between 40 volts and 60 volts to an output voltage of 6.6 volts to 10 volts. It uses EPC 2045 100 volt eGaN FETs in a full bridge configuration. The switching frequency is 1 megahertz, which enables the very high power density of 1700 watts per cubic inch, and the efficiency is 98.2%. The TI reference design covers the full solution to power a CPU. This consists of an LLC module, which converts to an intermediate voltage, followed by a 4-phase multi-phase solution that converts to 1.8 volts. The total efficiency of the 2 stages is 94% peak. This is one reference design that will be available soon from EPC. The part number is EPC9532. It is a synchronous buck regulator that converts an input voltage of between 40 and 60 volts to an output voltage that can vary from 12 volts to 20 volts. It delivers 250 watts, and the efficiency for a 56 volt to 19 volt conversion is 98.2%, with the temperature rise below 40 degrees Celsius. This is a different reference design, also available soon from EPC. The part number is EPC9148. It's a multi-level buck regulator that converts an input voltage of between 40 and 60 volts to an output voltage that can vary from 5 volts to 20 volts. It delivers 250 watts like the one we saw before, and the efficiency for 56 to 19 volt conversion is also 98%. With a temperature rise below 40 degrees Celsius. Multi-level configuration requires more components and 4 FETs, and it's more complex and expensive than standard buck that requires only 2 FETs. The advantage is that it allows a lower output voltage and that the switching frequency can be increased to reduce inductor size and height. As you can see here, the inductor is very thin, 3.5 millimeters in total height. This design features a microchip controller and a Worth inductor and will be promoted by EPC, Microchip, and Worth. We also have a dual-phase buck reference design featuring our EPC 2053 FETs. The part number of the reference design is EPC 9143. The input voltage can be set for 7.5 volts to 64 volts, and the output voltage from 5 volts to 20 volts. The default setting is 48 volt input and 12 volt output. In this configuration, the design delivers 25 amperes and 300 watts with 97% efficiency. The switching frequency is 500 kilohertz, and that allows 300 watts in the very small 1/16 brick format, which is just 33 by 23 millimeters. The design is scalable, and more phases can be added for higher power. Now let's summarize the topology choices by conversion and power level. The switch cap is inexpensive and very efficient at 48 to 12 volts for power levels less than 600 watts, but has limitations for higher power, and it's too complicated for 48 volts to 5 volts. The buck is the least expensive and smallest solution for 48 volts to 12 volts up to about 300 watts. Both the buck and the LLC have higher power density than switch capacitors. However, the LLC allows the best efficiency for over 600 watt applications for both 48 volt to 12 volt and 48 volt to 5 volt. And it's the best topology for V in V out ratios of 8 to 1 or 10 to 1. An EGAN based LLC for 1 kilowatt, 48 volts to 5 volts, or 48 volts to 12 volts is smaller than a 1/8 brick in size. For more detailed information about EGAN FETs and ICs in DC to DC applications, please see the 3rd edition textbook, GaN Transistors for Efficient Power Conversion, or view more videos in the How to GaN series. And for more information on EGAN FETs and IC products and evaluation kits, go to epc-co.com.